All right, so here we are, and this is the Rankine cycle for power generation, particularly in a thermoelectrical plant. And as you can see, this is the boiler where you burn anything that can be burned, whatever fuel you can use to burn here. That will produce steam. Steam will get into the expansion machine, which in this case is just a turbine. Could be anything else. Could be like a piston engine expansion or so, like in a train or so, like it used to be. And that shaft power that is produced from the turbine from the very hot vapor expanding here will produce this shaft power that will move like for example, a generator here as shown here, and that will produce power. So the power from the turbine will generate the power that is coming from the generator. And now the exhaust from the turbine or the expansion engine will be, go to the condenser where all that remaining vapor will be condensed and then pump back again into the boiler. So this is what we call the Rankine cycle. The issue that we want to solve now is how can we analyze a very simple this in an ideal case, meaning that the expansion in the turbine is fully adiabatic and reversible, right? That's a very important concept that we want to tackle here. That whatever is expanding here, it is done from an adiabatic and reversible point of view. With that said, let's say that condition one, the pressure is 500 psi, absolute. Remember that letter A back there, absolute. And that the T1, that's the temperature here coming from the steam, is 600. Obviously, this is superheated vapor. We will check the number in a second. Now, what we need from that condition as well, now that we have pressure and temperature, is the entropy. But also we need the enthalpy of that line. Now, for the exhaust from the expansion engine, which is in this case is just a turbine, we need the output pressure. That will be about 16 pounds per square inch. Absolute, again, about 1 pound or so above atmospheric pressure. Now, we don't know the temperature, we don't know the entropy, and we don't know the enthalpy of that line coming here. What we're going to do is how can we get this information very easy from a steam table. And the second part is what is the flow of our working fluid. In this case, our working fluid is just water, right? Water in a vapor state here, but now water when it comes from the condenser in a liquid state, and then it's pumped back again to the boiler to start the cycle. So the main point here is how this little amount of information, we can get everything about what is the efficiency from the power generated at the turbine versus the amount of power that is required in the boiler. All right. With that said, let's work out some very simple scenario here. And first of all, let me get this perhaps a little bit smaller. And let's get from the steam table. I have a program here that will do the calculation for you very easy. The important thing is that you get the right condition, and we know that this is superheated, but we will see in a second. For example, get here. Now, temperature, it says that is 600. We punch the 600 here. And the pressure is 500. So we put the 500 pressure here. Now, metric or English. Obviously, you change here, and the metric side will be that the temperature is centigrade and the pressure is measured in bar. You cannot change. That's it. That's what this software will bring to you. Either metric in this kind of units or English in this kind of unit, which for me is okay because this problem is right within the English side. So that would be 500 psi, no problem. It's right here, and the temperature 600. That's it. That's the unit. Now, the next thing that we'll do when we work this out is just calculate. We calculate. And now, as you can see, you get all the numbers that you need for the study of your Rankine cycle, which in this case, it tells you very right away that the steam quality is superheated. At the condition that we are punching in is vapor that is way above saturation temperature. All right. Now, the next thing, it tells you other information, like for example, the volume, the density of that vapor, compressibility factor, enthalpy, and entropy. These last two are very, very important for our analysis. So what we can do is very simple. We can copy the whole information. We can do this. So we have it on hand. Shift, print screen, will capture the whole thing. Now let's go to Excel for a second, and let's actually, before I'm going to Excel, so this looks better, right? Let's do this. We can do this and copy what we really need, which is this table at the condition 1. So that's what we need. We go to Excel now and we punch that there in Excel so that we know, like for example here, we are talking about pressure 1, temperature 1. We need, let's fix this so it looks better. And let's increase the size. All right, so pressure 1 is 500. T1 is 600. Now, here's the story. The entropy is on this point 1.559. 1.559. And the enthalpy of that line, enthalpy 1, on that line is about 1298.63. 1298.63. That's it. We worry about the unit later on, but that's the point. The point is that that's what I need to get all the information that I need for condition 1. Now, this is the part that is very important. I can make this smaller now that I see the numbers. I'm going to leave that there. That's condition 1. The important thing is what is condition 2. We're going to write that down. We're going to put the table here nearby. So let's go back again to my PowerPoint here. And let's take a look. Now, condition 2 on this problem, we've been told that the pressure, discharge pressure, is 16 pounds per square inch absolute. And here's the story. This turbine of this expansion engine will do so adiabatically and reversible, meaning that the entropy of point 1 is the same as the entropy in point 2. That's a very, very important concept because that will allow us to have two conditions on this side. When you have two conditions, then you can go to the steam table and get what are the conditions of point 2 with respect to, like for example, temperature, the exit temperature, but also the enthalpy. When you have the enthalpy of point 2, since you already know the enthalpy of point 1, that difference of enthalpy is the amount or power eventually that can be calculated coming from the turbine based on what value you expect to generate from here. So if you have this number, then you can calculate the amount of let's say kilogram or pounds per second or etc. that you need to recycle through the system. All right, so we know that we need this pressure to 16 psi, but we also know that we need to establish that this condition 2 will happen when S1 is the same value that we calculated before. If we move nearby, S1 is 1.559. So what this means? Now let's put this here, meaning that P2, pressure 2 in this case, is going to be 16. Temperature 2 at this point, I don't know what it is. We don't know. S2, we do know that one. It's going to be 1.559. Now, H2, we don't know that one yet. All right, so we don't know that. So let's go back again to our steam table. And here's the trick, the nice trick about this. For example, let's say the first thing that you might want to think about it is that the vapor coming out from point 2 might be saturated. It's a vapor, but it's saturated. Now, if it's saturated, we can go right here and let's say there's two conditions that you can put. temperature or pressure? Which one's going to be? Obviously, it's going to be pressure because that's the information that I have. You put a 16 there. The next thing, you leave that in vapor. When you hit the calculate, you check the entropy at that point is 1.74. It cannot be vapor, not at all, because I need a lower entropy, 1.559. You see what I need versus where it is, 1.74976, too high. This is not vapor. Would be liquid. Hit liquid. Calculate again. When you check on liquid, entropy 0.318, too low, cannot be liquid. Now you know. Well, if it's not vapor, if it's not liquid, definitely it's a two-phase system. That's where we are. The pressure is so low coming from the turbine or the expansion engine that there's some water on it. So the quality is not 100% vapor. It gotta be less than that. So I can show you what number you need to punch here, but it's a number between 0 and 1. If you put 1, let's put 1. Well, that means that it's pure vapor. So you will end up having an entropy of 1.74, I believe that was the number. Yeah, 1.75. Now, if you have all liquid, meaning you have a 0 here, calculate, but you end up way back again to entropy of liquid. So it's a number that is between 0 and 1. I mean, you can guess, you can start to mess around here with the two-phase until you see that the entropy here is, is the number that it should be between either vapor or liquid. Now, there's an easy way to do this, which is let's calculate what is the entropy at 16. That's the pressure. That entropy is the entropy. Let's calculate again here. There we go. That entropy there is the entropy of vapor, 1.75. We can write that down here. Like, for example, the entropy S2 for pure vapor. I'm going to write the word vapor here so we know what it is. The entropy of pure vapor in this case is 1.75. Now, we go back again to this and we said, how about the liquid one? Calculate. Again, at the same pressure. Well, that would be 0.32, just to make the life easier. So S2, if we have all liquid, on a liquid phase, then it's about 0.32. So the number that we are looking is the 1.559, which is in between these two. That means there's a formula that I'm going to write it here, very simple to use, that says the entropy, I'm going to write, the entropy for the mix is going to be equal to the entropy of the liquid. Let's put the L, it doesn't look good, like this. Let's write like that. The entropy of the liquid looks better, plus the quality of the vapor, let's call that X, multiplied by the difference between the entropy of the vapor less the entropy of the liquid. Close that parenthesis, and that's the formula that we're going to use to calculate X. That's the X that we need to put back here. When we are in the two-phase, that's the X that's going to be put here. You can guess, you can start to mess around with it. Like, for example, let's say that's 0.8. Calculate. Well, 1.46. We need to hit the 1.55. So let's have about 0.9. Calculate. It's above 1.60. I need 1.55. So you can see that it's between 0.9, maximum 0.8. It's a number. It should be a number between here that will make the entropy, the exit entropy from the expansion engine, the same value as the input. How about we use this formula? Now let's work this but for X. So in this case, X, which is what we need to calculate, is going to be equal. I'm just doing here the symbolic math so you know what I'm doing. Put a parenthesis here. That will be the entropy of the mix minus the entropy of the liquid, and all that divided by the entropy of the vapor minus the entropy of the liquid here. Liquid, yeah. All right, so let's see. Close the parenthesis, perfect. So you have this minus this in the numerator, and eventually this end up being in the denominators to put the equation in terms of x. Now, let's do the math. In this case, the quality is called x. Let's delete everything else. We don't need it. X, and we put here the math, equal. Now, here are the numbers that we need. Put a parenthesis. We do exactly the way it is here. The entropy of the mix is this one, minus the entropy of the liquid, which is this one. And that, we divide that by the entropy of the vapor minus the entropy of the liquid. And that's a number that should be between 0.8 and 0.9. That's it. 0.86643. Perfect. But that's the number that we need to punch in our system. Let's go back here. And this is the number that we need. So let's find out what's going to happen. Now we go 0.86643. How about that? Two-phase, 16 pounds, absolute, calculate 1.5586, 1.559. It's just perfect. 1.559 actually. At 3 decimal places. Excellent. So now we got that straight. Now that we got that straight, we can calculate everything else, because basically for condition 2, getting the temperature will be just as reading from here. So 216 is the temperature, 216.27, 216.27. That's the saturation temperature. And the enthalpy, going back here, the enthalpy will be 1022.68. 1022.68 here. 1022.68. We got that. Now we have completed our mission, that is to calculate all the conditions from 1 and 2. And now the next step is very simple. Like, for example, let's say that, let's go back to my Rankine cycle, that the amount of generation, the power at the generation level is a number. Let's say, I don't know, 10 horsepower or something of that nature, you know. And that amount of power, the only thing that you need is what is the efficiency of the generator. For the time being, let's say 100%. I don't want to get involved deep into this generator business, but they are very big. They are good. I mean, easily they can hit the 90s and above that, 90% efficiency between the power that is input here and the power that is coming out from the generator. Now, what I'm more concerned is, let's say, for the time being, that the power at the turbine level here, or the expansion engine, is about 10 horsepower. We want to make the number very simple. Why 10 horsepower? Let's say that you want to make this for your home. Typically a home, 10 horsepower would be good enough to move a house. So let's say that the power from the turbine is 10 horsepower. Now, we need to calculate the amount of the water that's going to be cycled through the system. You know, water being our working fluid. So the first thing that we need is to understand an energy balance around the turbine. So we have an input here. We have two output. One that is a shaft output, and two that is a mass output. But it's extracting. There's some energy coming out of the number two. So you have one in shaft power coming out, and also mass coming out from point 2. If we do a mass balance or energy balance, in any case in here, it's going to be something. Actually, let's close this a little bit more so that we see everything the way we want it. All right. So let's see. So we need to do a energy balance around here. So basically, let's do here. So what we'll have is a flow. Let's call m dot a flow, whatever it is. M, it's hard in Excel to write the point above the m, but it's flow, mass flow, times the enthalpy of that line. We know that our enthalpy is H1. Now, that is in minus whatever is coming out of point 2. That would be the same mass, flow mass, coming by the enthalpy 2. So energy in, energy out, or power in, power out, but also this is out. So you can say minus power shaft, power shaft out as well. And that should be 0. Again, we are saying that this is adiabatic. No heat coming out of from this process. Now, P shaft, we know that P shaft, or the power at the shaft level, is, we said, it's going to be 10 horsepower. That's what we're saying. Let's get the equal here because it's going to get a little bit confused. It's 10 horsepower. So now, there we go. That will do. So the question is, what unit I'm using here? And that's where the unit come very important. As you remember, I can move this somewhere here. I'm using BTU per pounds, meaning that this horsepower gotta go. This and the unit that I'm using right here are not compatible, so something need to be changed. Either horsepower to BTU, or decide, make your mind. Let's change the horsepower. So P shaft is gonna be converted now. I can use anything, like for example, I can use watts, but again, I'm using BTU. So the best is to convert this to BTU per second. If I remember right, basically you can say that 10 horsepower, if you multiply that by 0.7 average, that would be, that number there is about BTU per second. How we know that, right? You want to know that? That definitely is about 0.7 something. Oh, it's easy. Let's go to Google and let's put 10 horsepower to BTU per second. Here we go. And you get the number. 1 horsepower is about 0.7. See? 0.697 BTU per second. That's it. That's all what you want to know. About 0.7. So you have 10 horsepower, then you got 7 BTU per second. No more than that. This is straightforward. So close that up. So that's why you see the 0.7 here per horsepower for the conversion. So now you have 7 BTU per second. That's perfect. So now we can take this equation and work that equation for the mass M. Let's work that out that here. M, in this case, is going to be, and so let me do the math here. It's going to be, actually, let me do this in this way. That's going to be P shaft divided by the difference of enthalpy 1 minus enthalpy 2, close parenthesis, and that's where you get your M. If I do now the numbers here, P shaft, which P shaft you're going to pick, 10 or 7? Obviously, you need to pick 7 because so that the unit cancel out and you get mass flow. So that means I gotta take the 7, I'm gonna divide that by H1, and that H1 comes from here minus H2. That's come from here. Close that up. And that number is approximately the mass flow. That would be BTU, that would be pounds per second. That's flow, mass flow. Excellent. Now that's the amount of mass that I need per second to go through the whole system. I mean, it could be a little bit more because I'm assuming that this the expansion engine is adiabatic reversible, which is not. it has some efficiency, maybe about 70% or so, the turbine. So it's a different number, but again, it's just something that that allows you to do a very quick calculation where you are with this kind of a Rankine cycle. Now, that's the mass flow. Period. That's it. You don't have to do anything else. Now, if we want to calculate very quickly the efficiency of the system, we need the amount of heat that we need here. And for that, it's as simple as trying to get condition 4. What will be the condition 4 for this system? The condition 4, let's expand on this more a little bit. Let's say that the pressure drop, maybe you drop about 2 psi here in the condenser, could be more, could be less. It's not a big deal, but let's say that the pressure drop on the condenser and eventually the pressure end up to be, I don't know, 14.7 psi, and the temperature. Here's the very interesting story. Temperature at that point, sorry, it's not 0.2, but that would be 0.3. 0.3, and the temperature at that point will be the temperature of it will depend on the temperature that you've been using. 10 degrees above this, very easily you can get. Like for example, if the water that you are using to condensate this vapor is about 90, so your temperature here would be, the coming out would be about 100, 10 degrees difference. So I would say more or less about 100 degrees Fahrenheit. That's the exit temperature. So you got water, which is at 14.7 psi, and a temperature of 100 degrees Fahrenheit. So you are going from this condition to this now condition. What would be condition 4? Condition 4 the pressure has to be basically the pressure of the boiler, and that has to be about 500 psi easily. If not, we are in trouble. So we need to go back to that pressure. And what would be the temperature of 4? Well, there's some little amount of heat that you get from your pump when you pump this material from 3 to 4. I will not consider that at this point because it's very, very small. So at this point, the only thing that I will say, hey, the temperature here of 0.4 will be the same at 0.3. So let's say that the temperature of 0.4 for this case is going to be about 100 degrees Fahrenheit as well. That's it. All right. Now, with that said, so the amount of energy that I need to input here in the boiler will be the difference between 1 and 4 multiplied by the flow that we already calculated, which is about 0.02. Let's do the calculation very quickly. The only thing that I need is about 0.4, which is 500 psi and a temperature of 100. So let's bring my table here. And now where we are, well, careful. 3 and 4 are basically for water. That's it, for water in a liquid state. Now, what's the pressure? You can get right here because you will be in a super cool condition. Let's say that the pressure is 500, but the temperature here is going to be 100. And now we calculate, and clearly said you are in subcool region, and it tells you all the information that we need, and the most important is just the enthalpy, which is about 69.35. So we write that down here. That condition 4, the enthalpy of condition 4, which is, I can use, I'm using cap letter. I'm going to keep it like that for the time being. So the enthalpy here, as I was saying, is about 69.35. So 69.35. You can write the unit later on, but I'm kind of trying to make this video as short as possible. So that's the enthalpy at 0.4. So the question is, how can we get the amount of heat that we need to, get into the boiler? Oh, that would be, again, you just do an energy balance. So now, and this energy balance will be something, let's write it here. Like for example, the energy coming from the boiler, we can put Q boiler plus the energy coming from the mass flow here at point 4 because it's getting into the system. That would be then the mass M multiplied by the enthalpy at point 4. That's 2 are getting in. Now, this is coming out. So that means that this is going to be minus M times the enthalpy of point 1. That close our energy balance, and that should add to 0. So the only thing that we need to do here is to make this equation from the point of view of Q boiler. In this case, I think that I wrote this wrong. Boiler. Oops, let me write this right. Q boiler. There we go. Now, meaning that Q boiler equal, we delete everything else, we don't need it, here. You know, it's just getting these two parts here, one is positive and one is negative to this side, meaning that we'll end up like this one, but we'll end up, if I'm writing just for demonstration of the math here, it's going to be M times H1 minus M times H4. If I do now the math equal, the mass so is a number somewhere here, is this one times H1, we look for H1, minus the mass again time H4 right here. Enter, and that would be the energy Q boiler in BTU per second. You see, that's the amount of energy that we need. We need to burn something that will generate about 31 BTU per second. That's the point. What can be burned here? I mean, anything. Think about any fuel that you can burn, and you can get now, if you know the combustion amount of heat that will generate from that combustion, then you can get the amount of, say, liter per second of that fluid that need to go in, so to that generate that heat that we need in the boiler. But at this point, the only thing that I'm interested is in the efficiency of this Rankine cycle for my kind of a home design Rankine cycle. So what would be the efficiency? In this case, the efficiency, I'm putting an N, but it's more like an eta. Let's write then efficiency for my system. It's gonna be the amount of power that I'm producing is just 7 BTU per second. That's it. So we're gonna put this 7, and we're gonna divide that by this 31. This is the amount of heat coming, that you need into the boiler, but that is producing only 7 BTU per second. You are burning 31, but you're only coming with 7. The efficiency is going to be, I'm saying probably, it is less than that, but this is just a working number. Let you know where you're going to start with. So that multiply by 100, about 22 at this point. If the condition, for example, of P1 and T1 increases, the efficiency will get better. Actual Rankine cycle, these conditions are higher than the one I'm showing here. But the idea was to make this more for a home. If you are burning something around your home, and you can get this amount of energy in of the, what it was said, 31.183, then you can get an efficiency of about 22%. And then there's going to be a lot of heat being removed here, because you need to condensate all that vapor back to liquid so that you can pump it back into the boiler, and you can start your cycle back again. So again, that kind of, let me open this big perhaps so you get the whole picture. And that is as simple as it can get. Condition 1, condition 2, after the expansion engine, then you do some math just to ensure that if you are in the two phase, you can calculate the quality, meaning that this number here, 86, is 86% vapor, the other 14% or less is liquid, drop of liquid within the vapor. The next part, be careful with the unit or P shaft, or the power from the shaft. In this case, it's 10 horsepower converted to BTU per second. It's about 7. And from there, you get the mass. This is important. When you get the mass flow around your Rankine cycle, then you can calculate everything else, like the efficiency for the whole system. But then you need to figure it out. What is the enthalpy at the entrance of the boiler? Which basically, going back here, we said, well, the condition of the pump is very little, that we don't need to worry about it. And it is indeed something that very, I mean, you need power, otherwise the pump would not work. But compared to what's going on between the here and the boilers, this number is very small, even compared with the condenser as well. So again, that's the assumption that I did from 3 to 4, that the pump power here is pretty much negligible. Well, that's, folks, it's the end of this. If you want to tell me more about it, or you have any question, just let me know. As I always said, be careful, whatever be your final destination. Bye.